Okay, so I want to just go over two basic rules. It's important you watch it. There's this rule, which seems very confusing until you break down the basics of it. This question ultimately in logs, and this is how you must always think of logs, is what do I put as an exponent over b to get k? In other words, if this said log base 10 of 100, it's asking what exponent do I put over 10 to get 100? Clearly, the answer is 2. If I then turn around and put that 2, for instance, if this was written like this, if I then turn around and find the result here, which is 2, and then put it over that same base as an exponent, I'm simply reversing the process of what I just did. And it's clear I'm going to get whatever the result was that I was searching for in the first place. In other words, this exponent of a log, they simply cancel each other out, because this is finding the exponent that you would put over b, and then it's putting it over b. So of course you're going to get whatever you were looking for in the first place as a result, no matter what, because this process finds the exponent that you would put over b, in this case 2, to get k, in this case 100. And if I then take that exponent and actually put it over the b that I was looking at in the first place, I'm going to go full circle and get the 100. So this process negates each other, as does this process, which is essentially the rule that they were giving you before, which is this. It's the same rule. It's just they're reversed, right? These rules are equivalent. So of course, if I find whatever the exponent I need to put over b to get this result, it's clear the exponent I need to get that result has to be the same k. This is the reverse process. If I find the exponent of that I need to put over k here and then put it over the same b, I am of course going to get my k. These are actually the same rule, just this is with log as the exponent, and this is technically with b of k as the exponent. It's sort of hard to see. It's sort of up there, but it's the same rule. Now the second thing I was trying to express to you, but failed miserably, was if I had a log of 3 of 81, which I know is the answer 4. What do I put over 3 to get 81? It's 4. How do I find the equivalent log? Well, for 9. 9 is the square of 3. So you can just apply the square of 81 to get it. And the reason this works, the square of 81, 6561. Is it 61? I think 61. The reason this works is because if you look at this here, if I were to square that, and I were to square that, in other words, I don't affect this at all, I have successfully made the equivalent, because logs are always saying, what exponent do I put over this to get that? Well, if I add a square here, as I do here, then all I have to do is add the same square here to essentially negate, because that's just an exponent over that, and that's just an exponent over the thing we're looking for. So this essentially just puts a square over the result that I'm looking for. So to put it a little bit more simply, how would I make this is true? It's 4. If I square this, which is 9, the only way I can get a 4 out of it is if I square this. Otherwise, the answer is now 2, which is a square root down from what I was looking for in the first place. So the simplest rule is to make this equivalent, since you know base 9 is the same as 3 squared, you simply have to square this result. 6561, was it? Now they will match. This is true no matter what you use as a base. It makes more sense when you work with base 10 because it's easier to see. Clearly, the answer here is 3. So if I square the result over here, or the base over here, I must square the result up here to get the same 3 answer. And you will discover, yeah, it works. And that's simply because we're finding the exponent that goes over this to get that. If I've squared the exponent that I'm looking for, or squared the base I'm looking for, then clearly I must square the result, because 10, so let's say this, you got the answer 3 here. Well, because this is squared, 10 squared, 2 times 3 is 6, so it would have to be 1,000. And, well, that's a bad way to explain it. The method I just showed you, it works. Now the reverse is true, even when the numbers don't work. If I wanted to find the, go backwards, and I knew the log of base 9 of 6561 was indeed 4, and I wanted to find the log 3, clearly I've square rooted this, so I just need to square root the 6561 in order to keep the answers the same. Turns out the square root of 6561 is 81, and it all works out. But that will work out even if those numbers don't have a true answer. Let's say it's 3,000, so there's no whole number here. I can now just say, okay, well, the log base this is going to be the square root of 3,000. I can also do this. I can say, okay, well, it's going to be the square root of 3,000 is 3,000 to a half, which is the same as a square root. I can now take that half and put it in front and just say a half times the log base 3 of 3,000 is equal to the log base 9 of 3,000. Now, how do I prove this is true? Well, in my calculator, if I do log of 3,000 divided by 9, divided by the log of 9, I will get this answer. That's the base rule. So 3,000 log divided by 9 log. I get this awful number. I'll just kind of... Now let's find the log base 3 of 3,000. And I can either find the square root, or I can do it like this. So let's find the square root first. And to do this, I do the square root first, and then find its log, and then divide that by the log of 3, and hit equals. And look at that, I get the same number. Or I can just find down here the log base of 3,000 divided by the log of 3, and then multiply by a half to get the same answer. And that's because these are all logs reveal the exponents. So all I'm doing is manipulating the exponents of my results.